Hello, hi everyone, welcome to lab session 5, and here I've logged into my Ubuntu system because from now on the way we are going to interact with our FPGA boards is through Ubuntu system. You might have already gotten your system installed with Vitis, Vivado, Vitis AI, and we'll be exploring all these things, and if certain bottlenecks come, some of us will be there to help you out. So let's first of all begin actually by booting up the FPGA. So here you can see that I have my FPGA with me, and as always I've connected it with the keyboard, mouse and the internet connection. This SD card image which I'm using right now, this SD card image is actually, let me just clear up my desk because it's looking very cluttered right now. Alright, so I'm just going to boot it up, but before booting up you need to ensure that you have a JTAG port connected to your laptop or your computer. And let me switch over to my screen. So I'll just open the, alright. So in the Kria getting started guide we had seen booting up your starter kit, and inside that instruction for Linux. So this shows, this clearly says that we can do a D message and grep the TTY output. So what was referred to as COM port in Windows, the device management in Ubuntu is referred to as TTY. So I'll execute this command and show it to you. So I'll open a new tab, and the command is D message pipeline operator and grep TTY. So sorry, D message. Obviously this has to be executed as sudo because you're trying to access system files, and for your laptops which you own you might be doing the sudo password. For the system which you do not, you'll just can for go ahead with this TTY USB 1, like it's basically showing that it is connected. So the way to connect with the device is sudo putty, and then whatever the USB device this thing is connected on, so that is accessed through the file system. So TTY, you can directly actually copy it everything from here. So this signifies the baud rate, the parity bits, the number of the stop bits I think, and so this is the command which we have to execute. The only thing which we'll have to do is, instead of USB 2, we need to actually select USB 1, because this clearly shows that the second COM port should be the second number COM port corresponds to UART. So it should be TTY USB 1, and we can verify, like even if something goes wrong, we'll verify it. So as of now, this window has opened up in PuTTY, which is the serial communication. In Windows, if you're doing it, it's MOBA Xterm. So like in MOBA Xterm, you can it's basically trying to read the UART signals. So now let me switch to this view, and as soon as I plug into this, the outputs will start coming on my screen here. So like just start seeing, I'm plugging in this right now, and as soon as I plug in, I'll shift it. So the device has started to boot up and it's doing the auto boot. So just like we have a bootloader in our Windows laptop where we select whether to go to Windows or Ubuntu, similarly here also it's trying to boot from the MMCM1. MMCM1 device refers to the SD card device booting. Alright, there are multiple ways to boot up. So now this is loading, and the font size unfortunately I cannot increase, so just bear with this font. So as soon as we this thing boots up here, you can see that in my screen right here, the GUI has also opened up, and I can fully interact with this GUI with my keyboard and mouse. So that possibility is there, like I can go to the file manager and can open the file. So it's like a complete Linux system in itself. So let me shift back to the view, this view. So I'm guessing that you can run all these things which you want from your FPGA directly, but GUI is something which we are not too worried about, because our accelerators and software and everything, that will happen like, you know, inside the memory. And the HDMI port, instead of using it for displaying the GUI, we'll use the HDMI port to display the FPS of our machine learning model or something like that, right? So here, one thing which you need to actually know is the IP which your board has been assigned. So if you just type if config, so you can see that the board has been assigned the IP, like in Ethernet. If you've connected through Ethernet, then the inet 192.168.1.0. So this is the board, this is the IP which we'll need to connect to the board in any other way. So I really like the VS Code's way of connecting to the board, so I'm displaying it again. So I'm keeping everything very raw here right now, and want to show you everything how it is done. So we can go to the remote settings, and we can click on SSH. So it will just install certain extensions, because this is a fresh installation of Ubuntu which I've done on my system. So you can click on configure SSH hosts, and for the alias you can type Kria Linux. For the host name, you can give in that IP address which we just saw from the output of the putty. What's the command for copying from here? Let me see if this works. Okay, so copying from there is difficult. I'll just type it out, 168. There are certain shortcuts I'm not knowing exactly which one, so I'll just type it out, 1.10. All right, let me just verify once. All right, and the user we're going to log in is as root. So we'll just save it, and now once we click on connect to host and click on Kria Linux, so it will ask us, do you want to verify, enter the password for root. So since there is no password set for the root, we'll just press enter. Or is there a password set? Let me just verify it. So the password for root is root itself, and therefore I just typed root and it opened up. There is no user which is created. Everything what we're going to execute is going to be executed by the root. Root is the main user of the, like, you know, the topmost user, the super user of your Linux, and it can do anything basically with your system. Alright, so we are inside the file system. I'll just open the main root folder, and I trust the authors. So this is like a basic setup which you should be having, and I'll just open the terminal to show you. So now basically I have everything up and running with me. Like, I'll just open some samples. Let's open a sample of face detect, and so all these files which I'm reading right now are being served from my FPGA board. All these files are present there, and if you have downloaded the correct file for your Pita Linux, which I had shown in the last video, then you would be also getting the same thing. Alright, and now from this point onwards, we'll actually explore the Vitis AI library user guide, using which we'll, like, you know, all these libraries which you're seeing right here, and based on that we'll do some compilation steps and see how the machine learning model performs on this. Just a heads up that most of these files which you're seeing, like, you know, on the display here, right, anytime you can actually click on this and can access this as well. But if you do not have a keyboard or mouse, if you just have an Ethernet port on your device, like, you just need the Ethernet port and the JTAG port and the SD card and just power cable. So you don't need anything else to actually interact with your Kria or your FPGA board, and you can do all the things which you would want with your board. Alright, so for now I will just actually minimize these things. Now I don't need putty anymore. One thing which is which will be important for us later on would be this Kria dashboard which is available. So I'll just, when I do this bokeh application which starts running, okay, as of now it's not enabled. Anyways, we'll come back to this later. so don't worry. Or I can see this actually, like there's this slash user Kria dashboard. I'll just execute this command from my terminal. So we'll execute slash user and like we'll print ls slash user, and then in which folder it is saying bin Kria dashboard, in bin Kria dashboard.sh. So if we look at the contents of this file, it is actually a bokeh file. Control A, cat. So this is the file. In fact, I can open it on the VS Code just by typing, like, instead of cat, I can type code, and it will open here with all the, like, everything properly annotated and color coded. So we want to run the SOM dashboard, and for this it has to be assigned an IP address. So by this time this shell script was executing, the IP address was not assigned, but now it is assigned. So for that we'll just run this code. So slash user, like we'll just delete the initial part. So it says SOM dashboard will be running on this IP address, on this port. So now if we go and run this, so instead of localhost, we'll have to actually use the IP address. And now the hardware platform statistics, you can see the complete CPU utilization which is happening on all the A53 cores, the total free memory in KB which is available with you, and memory usage in percentage, the CMA used, the swap used, and the memory used, and the current, temperature, and the SOM power. In fact, you can see all the voltages of different parts of the board, the IO banks and everything. So this is really helpful in whenever we do research work, or like when we are running machine learning models, how this thing is changing, how much CPU is being utilized, and what core we are running. So all these things we can actually measure. And here you can see the frequency at which the CPUs are operating. So alright, so with this information, let's actually get started with the documentation. So the documentation, one thing important which I have to do is go to the 3.0 version, 3.0 English version, and the UG1354 is the guide's name, and it is Vitis AI library user guide. Besides this library, we'll use one more which is UG1414, and this document is titled Vitis AI user guide. Alright, so both of these are similar but little different in nature. So first of all, we'll actually explore Vitis AI library user guide, and you'll understand that why am I telling you in a minute. Okay, so let me just check out whether my tool is okay. It's working fine. Let me shift to the rectangle mode. Sorry. Alright, so I just finally figured out that I had to make some changes in the configuration file to draw these rectangles. Okay, so alright. The following Vitis AI libraries are related to this document, so I'll just read this along with you, and I'll stop at the important points. So let's just look at the document navigation, that what all things we are going to cover. So it's an introduction, then talking about installation, some libraries and samples, some programming examples, some application demos, and then programming APIs, calculating performance, and some API reference. So this is what the table of content is. The introduction provides a high-level overview of the Vitis AI library, and this chapter provides a clear understanding of the Vitis AI library in general, its framework, supported networks, and supported hardware platform. Installation tells how to install the Vitis AI library and run the examples, and this is what will be important for us. The information in this chapter will help you quickly set up your host and target environment. Now, if you remember the discussion which we had on the GPU board as well, host refers to the computer which I am right now, or your basically the CPU based, your laptop, etc. And the target environment refers to our FPGA. And we'll see how to compile and execute the Vitis AI library related examples. Libraries and samples describes each model library supported by the Vitis AI library. And this chapter provides the understanding of the model libraries supported by this Vitis AI library, the purpose of each library, and how to test the libraries with the images or videos and calculate the performance. Then we'll see some programming examples that developing applications using Vitis API, developing application using your own models, customizing the pre-processing step, using the configuration file as pre-processing and post-processing parameters, and using the XDPU tool for DPU and X model debug, and implementing and registering custom operators. Alright, so let's scroll down. Okay, so what Vitis AI library is a set of high-level libraries and APIs built for efficient AI inference with the deep learning processing unit. So this deep learning processing unit which you see is actually where we're going to run all our models, all our machine learning models, and more on this would be coming in the theory lecture as well, but as of now we're just going to use it, and based on the Vitis AI runtime, and it supports XRT 2022.2. so XRT stands for Xilinx runtime. So any software package which you come and any hardware accelerator which you're building, it has to have its own runtime. It simply refers to the software support. So the Vitis AI library provides, an easy to use and unified interface by encapsulating many efficient and high quality neural networks. So you'll see a list right now that of all the neural networks which are supported by this. And this simplifies the use of deep learning neural networks even for users without knowledge of deep learning on FPGAs. The Vitis AI library allows you to focus more on development of your application rather than the underlying hardware. So the Vitis AI library has 4 parts as shown in the below block diagram. Let me zoom out a little bit to have the complete, or actually let's begin from the bottommost part of this, the AMD FPGA platform. So AMD FPGA platform is where you'll finally be running all your tasks, and the way to interact with your hardware is through this XRT, the Xilinx runtime which I was telling you. So it's like a kernel layer which sits between your application which you're writing and how it's going to interact with your final hardware. Now the base libraries are the libraries which provide the basic programming interface with the DPU. So they are coming in 3 flavors, CPU task, DPU task, and XNN PP. So DPU task is the interface library for the DPU operations, and CPU task is the interface library for operations that are assigned to the CPU. So any machine learning problem would have 2 parts to it. We'll be doing some things on the CPU and then accelerating some things on the DPU. Like the basic machine learning part, we'll be accelerating on the DPU. So it consists of CPU task, DPU task, and XNPP refers to the post-processing library for each model with built-in modules such as optimization and acceleration. So these are the base libraries. Now on top of base libraries, we have the model libraries. So in that you can see that we have certain classification tasks for, like, we have the classification tasks, the single shot detection tasks, all the YOLO, V2, V3, V4. This is object detection, then poly-P detection for some polygon mappings, semantic segmentation, like you cannot just, like, if there is an image, you do not just draw the bounding boxes in that image, but you actually make a segment of that. And SAM-V2, there is a model. I'll just quickly show it to you, SAM-V2, because it's one of the most interesting models which is out there right now for doing segmentation. So it was hardly introduced, I think, 1 month back, and you can draw masks on videos itself. So you can do all sorts of segmentation tasks. Definitely SAM-V2 has not been implemented on FPGA as of now, and it's an open source model, but it requires a huge deal of effort to actually put it on FPGA. So if some of you is too much interested in this, then they can go ahead and take up this project, and it will help you a lot. Like, it's going to be a huge research if you're going to do that. Anyways, getting back to our documentation. So we can see certain pose detection tasks and open pose detection, hourglass, face detection, face recognition. So not just we'll be doing the face detection, but we can actually recognize the faces. Like, We'll not be only able to detect the face but recognize, okay, this is the face of another villain. So yeah, every time I come it will recognize my face. It can be used for certain applications like what you've seen is as DigiKey or DigiYatra, which is installed on airport. So, for that kind of tasks you can do face recognition, finding face quality, certain face landmarks, retina face, re-identification detection. RAID stands for re-ID, that if there is a face which is registered and again that face comes, so machine learning model knows that which face it is. Similar to face recognition, but it's more about re-identification. And again, plate recognition, plate detection, road line detection, multitasks, COVID-19 segmentation, medical segmentation, point pillars, and there are many examples which we are going to see actually. And you can run any of these tasks, which will be one of your tasks in the tomorrow's lab. So we'll be assigning you certain tasks, and we'll give you the sample images and videos, and you have to run that and upload it on the Google form. So these are the model libraries, implement most open source neural networks, including common type of networks such as classification, detection, segmentation, others. These libraries provide an easy to use and fast development method with a unified interface. Now the library samples, so the library test samples are used to quickly test and evaluate the model libraries. So in order to evaluate the model libraries, there is this library sample which can help you do a JPEG test or a video test or do the performance and accuracy tests. And there will be application demos to show you how to use the Vitis AI library in your application demo. So there will be like a multitask demo 1 and multitask demo 2. All of these things are available in the Vitis AI GitHub. Like I'll just walk you through the repository one. So this is the main repository, and instead of the master branch, we'll go to the version 3 branch. So we'll just go to the version 3 branch because this is what we're checking out the documentation for, and as of now the board which we are using, that is supported only up to version 3.0. The latest boards which are coming, they are coming with version 3.5. So inside this, if you go to the examples and the Vitis AI library, and you'll see the same structure here. Apps, so these are the applications which you can use: multitask, segmentation, and pose detection. Besides that, there'll be certain samples for you, and which we just seen, like most of these samples like face detection or something. So if I open this, then the test accuracy, test JPEG, test performance. So all of these are what? All of these in your documentation, these are your library samples. And the model libraries themselves are actually available in a different repository. That's, I think, inside the source Vitis library. So here if I do the face detect, the same folder if I open, so these are the files like face detect.cpp, detect underscore imp.cpp, and sorry, let me again go there. And this header file, face detect.hpp file, which is nothing but like just the header file for implementing the later on CPP file which you have. So we're just including this file here, and so it refers to the model libraries. So I hope you understand where are all these libraries, and the base libraries like the CPU task, DPU task, they are also available. You can find them in the same like if you just search for here, search somewhere here, you'll find CPP task, DPU task, like sorry, CPU task. Let me just search for it. Yeah, here you go. So inside the Vitis AI source, Vitis library itself, inside the CPU tasks, you will see all the CPU tasks which are there. So these are your base libraries, and there are certain examples of this, like customized example, how to write a C++ class, writing add operators and all those things. So the world of embedded systems, embedded system engineering is very interesting, and it is just picking up with the advent of hardware accelerators. That's why we've designed the whole course centric to this, and while teaching you, I'm also getting to learn a lot. And companies like AMD, Intel, NVIDIA, they are at the forefront, and we are actually gaining skills which we'll be directly able to use in our industry, in our industry job. So don't get scared yet. This is like very simple sort of classes which they have made, and they have made all these things public. Certain operators they have made public. So XIR is just the Xilinx intermediate representation. So any operator which is there, it's having like an intermediate representation. So that's what this class is defining. Ultimately, what this operator, this custom myadd operator.cpp file is doing is making a very methodical way of creating operators for your intermediate representation, and it is just doing this add operation. But the way it is structured inside the VART and everything, it can be used as an operator for your machine learning acceleration tasks. Alright, so let's get back. So once we've understood this base libraries and everything, and just finally one thing was left, which was DPU task, I think. So let's see if we can find DPU task. Yeah, okay, here it is. So it is having the same nature as that of CPU task. Definitely you can include a lot of, like, you know, here you will see some header files of DPU task and what all tasks, like it just refers to your, you know, brief static method to create a DPU task. So this class is like, you know, just the DPU class, and then inside that certain functions are there which you know, for defining the mean scale values you can use this function, and like, you know, mean BGR image, or like all these function definitions are there along with their return value and a brief documentation about them. So with this header file you can actually figure out what you want to do, and then the main files are defined inside the source folder. So like it is again importing some tasks, so you can see, like, you know, DPU tasks. So here we are getting the definition of those function names which you were seeing earlier. All right, so no need to understand all of this code fully. Most important thing for us is how to actually utilize this code. So let's just jump back to this documentation. So features, the Vitis AI library features include a full stack application solution. Okay, and let me just bring out my pen. A full stack application solution, optimized pre-processing and post-processing functions / libraries, because any machine learning model does not run without some pre-processing or post-processing. So you have to have certain functions or libraries which do it in a very optimized way. It consists of open source model libraries. It consists of a unified operation interface with the DPU and the pre-processing and post-processing interface of the model. So just now we saw, like, you know, how some myadd.cpp was, this operator was created, which was like, you know, it had a unified operation interface kind of a thing for the DPU. And practical application based model libraries, pre-processing and post-processing libraries, and application examples. So the methodology which we are choosing is actually top-down approach. We're first of all going to learn how to, like, you know, utilize the pre-built things and like use them, and then we'll see how to actually construct them from the bottom up. So I hope, like, you know, it's making sense to you. Let's proceed forward. So Onyx models is something which we'll have a separate session. Onyx is a huge thing. It's a open neural network exchange. So what internally these people are trying to do is actually replicate Onyx, and Onyx is something which can run on any hardware accelerator. So it's like becoming an industry standard for hardware accelerator platforms. I'll just quickly show you their website, Onyx home. So Onyx is an open format built to represent machine learning models, and whether you search for NVIDIA, it supports Onyx. If you search Intel, Intel supports Onyx on their hardware platforms. Apple supports Onyx models. So you can convert any model to the Onyx model, and in fact if you go to the GitHub Onyx page and you scroll over to their examples, or I think their model zoo, they have a separately defined model zoo actually. Let me just search for their Onyx models. Yes. So it's a huge collection of pre-trained models from literally computer vision, natural language processing, anything like any model you can convert it to Onyx and can do your inferencing on that Onyx file. So you see the inception net is defined on offset 17, offset 18. So these are different versions of the operation sets which they have, and there are different models along with different model sizes, convolution mixer base and connext, CS3 darknet, darknet 53, CSP darknet, date model. So all these are date model is actually a very famous one, so I'm forgetting, it's a transformer model. You'll see Hugging Face, yeah, data efficient image transformers. So all these are actually like cutting edge vision transformer models which your ChatGPT is using, and they're running it on GPUs, and there's a whole bunch of research possible with just the understanding of Onyx and how to run those files, the operators which Onyx supports, and how to run it on an FPGA. So anyone who's wanting to do any research work can go ahead and explore this. Even I'm exploring myself, so if anyone wants to do a research on project on this, can approach me. Okay, so let's get back to this. So I've shown you certain breadths and different things. We've not gone into the depth now, but we've explored certain things. Now I think it's almost 30 minutes since we're into this lab and we've not executed something. So let's quickly start getting, besides the theory, let's start executing things. So we've already downloaded this img.gz file, and this is what we've burned, and that's why we got that FPGA board up and running. So this shows the model supported by the Vitis AI library, and all these Inception ResNet, Inception V1, Inception V2, MobileNet, ResNet, VGG16, single shot detection, MLPerf, MobileNet, SqueezeNet. So all these are mentioned with on which platforms they are supported. So most of these things you can see Y is mentioned in front of them. So it's a good thing that all of these models are supported for our KV260 board. And some of them are made on PyTorch, some of them are actually made on TensorFlow. So it's a huge list which we have here. So with suffix PT were trained on PyTorch, were trained on TensorFlow, and with no suffix were trained on Cafe framework. So now how to install the Vitis AI library. So we've already actually using the pre-built image and using everything which we have. We've already done quite a lot actually, but still I'll just quickly walk you over through this, that how we have to set up the host. So the host might be already set up for you if you're working in the IPC lab. If you're working on your laptop, then you need to set it up. So we have to visit the Vitis AI GitHub repository, which is this repository, and we'll clone this repository. So setting up the host device for the edge. So we're setting up the host device for the edge. Edge means that the FPGA board is kept right next to you. And there is another category which is called for cloud, for data centers, which is a separate category and a separate interfacing scheme. So we'll be interested in the edge deployments. So first of all, we'll have to git clone this repo. So we'll make a soft copy of this, because this Vitis AI repo is a huge repository, and if you clone the entire thing, then all the code of all the versions, previous versions, everything will come up. So there is a more effective way of installing this code on your laptop. So this repo has this Vitis AI repo has so many branches which you can see, and if you just git clone it, then all these branches, codes and everything will come. And for each branch there are multiple commits, there are so many commits inside each of these branches. So you can actually see the different commits which are being done, and each commit has the changes, file changes. So we do not want to install all of those things. So instead what we'll do is we'll do a shallow cloning, and let's actually, so this is the browser window where I'll just actually close this server, or maybe keep the server running and just open a new bash script. So this is the Vitis AI folder here is already having certain files inside it. So this is on the FPGA board itself, but since we want to actually see how to do this also, we'll git clone this. So I will create a new window. So now this is not this is not referring to my FPGA board. This is running on my computer. You can see that by this tag here. And I'll go inside the documents folder because I like to keep my repository, my things clean inside my operating system. So here you can see that I have certain ML projects, DB testing, and one of the smart QNAB, which is a backend code of one of the things which I'm working on. So here I'll do git clone, and instead of passing the repo directly, the repo's address directly, I'll just do certain things. I'll just say that I want to check out the branch by the name 3.0, and I just want to copy the single branch, so I can pass in this tag single branch, and I just want the latest commit, so the depth is I'm keeping as 1. And then what you can do is you can pass in this this URL. So this will be relatively quick as compared to if you would have tried to clone the entire thing. It would have taken you a lot of time. Like if you have time, I would certainly advise you to actually try doing that to see how much space we have saved and how much time we have saved. All right. So cd Vitis AI, and so this is the latest folder, and this is the exact thing which we were seeing on our GitHub page. Okay, so first step was to actually git clone it. Now moving forward, we'll go to the board mpsock and we'll install the crosscompiler.sh script. So cd board setup mpsock, and here you will see ls shows all the files which are available. So we'll download this host cross compiler script. Why cross compiler? Because again, as I told you, my CPU is running, let's say, i9 processor or any i7 processor or AMD Ryzen series processor, but the thing which I have to compile the code for is ARM A53 processor, right? So there is a fundamental mismatch. So the compilation has to happen. If I have to compile something on this host and then run it there, either I compile it on the FPGA itself. There also the compilation tools will be required, that what do you want to compile actually, for which processor you want to compile, but mostly it will have the compilation for its own processor. Here we'll have to download the cross compiler. So for that, I'll first of all make this executable by doing chmod +x and /. So once I've made this executable, I can execute this script, and it's downloading certain files. So while it is downloading, we'll progress forward because this is not like a bottleneck for us, because we have pre-compiled lot of pre-compiled examples which are already ready for us to run. So that's it, and it will install this Peter Linux SDK tools and everything. And yeah, I would just want to see this like it's already executing right now. I just wanted to see once that cd documents Vitis AI board setup mpsock. What was the content of this? Because the cross compiler will be installed by default and install path. Okay, so the default install path they have given as the home folder itself, which is alright, which is in fact better for me. So the home folder is this tilde sign followed by / which you see here. So it's installing that file, the Vitis AI installation path it's giving. So that's alright. Now the next thing would be to actually, how did I go on the top? Nonetheless, when the installation is complete, follow the prompts and execute the following command. So you'll have to source the environment, like once the thing is complete and ready, we'll actually execute it. So it's still installing. We'll before doing the cross compilation, we need to do this step, and then to compile the library sample in the Vitis library using classification as an example. So we've used classification. So we'll go inside the classification folder and we'll execute this build.sh script. So doing this build.sh script on my local computer here, like, I'll clearly show you what exactly, because this will give you a lot of clarity. So running this script inside the Vitis library samples and taking classification as an example. So this build.sh script, right? I'll open in terminal, code hyphen n dot. So code hyphen n dot refers to this repository, and hyphen n refers to a new window. So in this new window, it has opened with this classification thing inside, and even if I open a new terminal, I can execute directly something here. So like, practically this is VS Code is all what you require for your any coding or development work. So it is telling that for the classification tasks, you can choose the following valid model names. So you can use InceptionNet for doing your classification tasks. You can use MobileNet, you can use ResNet, you can use VGG16, VGG19, ResNet 50, SqueezeNet. So all these things we've studied in our lectures. If you notice, like all of, not I would say not all of these, but we've seen, like, how these models look like. So my purpose of introducing machine learning from the very first day was this, that we get a comfortable, like we are actually aware of all these things. It's not like completely black box for us. So I hope we understand all of these things, like what all models we can use. And these model names have one-to-one correspondence with the model names which you saw here. Like all those things which you are seeing there mentioned in this file are available there as well. And we'll use this build.sh script. So what is this shell script doing actually? So this first part, so it's not very difficult to understand bash code, like, with the help of ChatGPT also you can understand very easily. So we're having a variable called 0, and we're doing an AND operation of 0 with a function. So if this function defaults to true, then the result will be set to as 1, and if the result is 1, then we'll, and what is it that we're looking in this command? We're listing all the packages which are available. So if I just execute this package configuration list all, like if I do this thing here, so it has listed all the packages which are installed. And if I do this on the FPGA board now, so here you see that Cairo, dbus, epoxy, form, GDK, GMP, GMPXX, ICE, certain libraries for CryptoCrypt, and some photograph libraries, SQLite, Wayland for, like, rendering the GUI. All these things are mentioned here. All these C libraries are there, and inside, if we do not have an OpenCV4, then it will set flags to OpenCV3, like, the default. Right now we do not have even OpenCV3, so we do not have any of these things. So before compilation, we need to be sure, if we're compiling it on the host, that we install OpenCV4. So it gets also listed here. But if the same thing we execute on our FPGA board, so here a different set is there, and definitely there are a lot of files in here. All right, so instead, like, trying to manually see all these files, you can actually manually see all these files as well, like, what does each of these files do. But I'm looking for a specific file. So OpenCL is also there, by the way. It's Open Computing Language, generic installable client. Like OpenCL is used quite a lot in development work, and I'm not able to ball out OpenCV with my, like, I out basically. So let me just grep for it actually. So the same command which they have mentioned here for grepping, I'll use that command. Grep OpenCV4. So by this actually activity, I'm also making you um, conversant with some of the commands which we use in our so it has an OpenCV4 already installed inside the machine, inside the FPGA board. So the Peter Linux image which we've got, that has OpenCV4, so that it can, like, execute this build.sh script. And but on our host machine is not yet ready because it does not have all the files which are required to compile, like, all the packages which are required to compile. Okay, so let's get back to the host machine itself where we are exploring the code. Alright, so this is what build.sh file is doing, and then later on this is just doing the compilation step. So CXX, this part, like, we're using the C++ 17 and the version 17. This is how we are actually defining variables in our bash code. So we're setting it to G++, like -G++. So the file names which we are capturing, all the files we are capturing in the with the having the extension CPP. So by the way, Alt Z actually helps you wrap the code, like, instead of you scrolling to the right to see all the code, Alt Z helps you bring it inside one single window. And let me zoom in a little bit for you people. All right, so this is actually setting up the file and loops through all the, in the current directory, all the CPP files which it sees, all the CPP files which you're seeing right here, all these will be combined into a single executable which we'll run. All right, into a single executable which we'll run. And this flag which you see -0202, this is for actually the optimization. So this optimizes the code for better performance. -I adds the current directory to the list of the included directories, like whatever the current directory is, it includes that to the list of all the directories where it will find out, where it will use for doing the compilation task. -O specifies the output executable name. So whatever will be the base file name, that will be assigned as the file name, and all these files which you see here, they will be passed on along with the compilation. So we link various libraries needed for this Vitis AI project, and like this library which you see, L Vitis AI library classification. So this is just one library, -L Vitis AI library. Then Vitis AI library DPU task, what you like, we had already explored the XN in PP task, the Vitis AI library model config, the Vitis AI library math class, and the LVAR tutor, like, things necessary for like Vitis AI runtime library, the Xilinx intermediate representation, and P threads, and for, like, threading, and JSON log for actually logging all these things, Google logging libraries. And then the OpenCV flags which we had, like, taken here. So those OpenCV flags we'll set here. And OpenCV core, OpenCV video IO, OpenCV image processing, image codecs. So OpenCVs will be used quite heavily. So all of these finally will create a single executable file which you can execute, and you can read here in the readme file as well, that once you do this build.sh file with all the necessary files installed on your computer, and you'll get the test JPEG classification, which will be the base file name. Like, if you, whatever thing you are running, the test JPEG classification.cpp, that will get formed, or the base classes will be the output name, and you can pass in the model name. So from the list of the models which you had seen here, like, if I do Control F, you can see, like, it is mentioned in this here in the list of valid model names which we can pass. and you given it JPEG image. So that's all. Like the code is actually too zoomed out for me, so I cannot work in this way. And these are the results which you'll see. Like if we pass in a sample image, then it will classify, give it a score that okay, so the R index 109, so it's a brain coral, and the score which is assigning is 90% probability. Then 0.003% of coral reef and brass rock beauty, something like, you know, it'll define like that. And you can pass in a different thing to the same image, and you can see that how different models are numbering or classifying with different accuracy. So they've actually printed out for each and every model which is possible what the model has outputted, and we'll see that in a minute. So the performance, like we can also click on the performance, like how is this model performing, and we can pass in a list like test performance classification.list file, and it will run. So here you can specify the number of threads, and S is also signifying something, I think number of seconds, total number of seconds for timeout or something. We'll see later on. And we can check the accuracy as well and publish the results. Okay, so now actually let's try doing this classification task. Before, we'll just look at one small theory thing which is remaining. So we've set up the host, and like we can actually execute this command. So that's where, like, you know, from where I picked this up. To modify the library source code, we can go inside the source Vitis AI library, which I told you, like, you know, if we had the model library. So if you were looking at the classification library, let's say, like, you know, is there classification mentioned here? So one of these classification, the first one, like if there is a classification library, we can actually modify the code of this library, how this is executing, what pre-processing, post-processing steps it is doing by going inside the source folder. And from the library samples file, we are just actually, like, you know, we would see in the library test samples, we used to quickly test and evaluate the model library. So here we're just testing, like, you know, the C code which you'll see here is very simple code for testing. And if you have to make any changes to the model library, you have to go inside there. And yeah, that's it. And you can choose any of these models which you are seeing here, like, you know, obviously which are those which are valid model names. For that, you can choose any of them. So you can try building these examples, and this might be, like, you know, in some of the lab tests we might ask you to do this process, and you'll have to follow that. So one piece is remaining inside this, that where are these models themselves, like, you know, where are these model files themselves defined. So let's just quickly look at that, and after that we'll be probably done 70-80%, like we'll understand the full thing. So let's go inside the Kria board itself, and I'll do the ls operation. In fact, I'll open a new folder if possible. File, open folder. We'll open the root folder itself. And inside this, we'll go to the user space and libraries. Okay, so inside user, we'll go to the share. So you can see that how VS Code beautifully actually, like, you know, structurizes the code. And inside the Vitis AI library, so these are all where your models are defined actually. And since in this example we were particularly looking at this inception net, so here also let's look for this inception. What was the name again? Inception v1, like, you know, v1, v2, v3, anything would work. So inception v1, as you see here. So I'll open this in the integrated terminal and type ls. So these are all the files which are available, and you can actually, like, you can see the proto-text file, the X model file. So X model file is actually the binary file. You cannot see it exactly like this, but using the xdpu util tool. So this xdpu util tool is there, and you can pass in the X model to this, like xdpu util X model, and I think you just have to specify the model at this point. So dot slash dot X model. There is a way to actually list it. I think we'll have to pass in -l. Yep. So we'll actually output this to test.txt. So this operator basically means whatever you want to show the output on the terminal, instead of that, put it onto a file, and we'll open this file code test.txt. So now you can beautifully see, like, in a nice rendered format, in the JSON format, how this thing is structured. So this X model file is showing. We later on study what these subgraphs are and how these things, like, it's a huge messy space. I know there are so many things coming on your way right now, but you see that the subgraphs, like, inside this main big file, you have subgraphs mentioned to you, and so the first parameter in the subgraph, so it's a list actually, and the first thing inside this is the index and the subgraph data, the device, and for the index 1, so this index 0 is just defining the name. So index 1 is defining your subgraph, like what subgraph it is. So it is doing a convolution 1 with 7x7 kernel and a stride pattern of 2. The device name where it is going to run is DPU and not CPU. Like, it can specify, okay, this I have to run on DPU, this I have to run on CPU. The fingerprint it matches, it has to be the same fingerprint for which it is compiled, so that it does not. So DPUs are different versions, architectures. So it's like, X model file ensures that it is getting run on the correct thing, on the correct architecture. So in our case, this is the architecture i7B4096, and workload, the input tensor which will go inside is images of size 224 cross 224 cross 3 in inception v1, and fixed position we're keeping as 1, and the output tensor is of shape 1000. It'll define into 1000 classes. This fixed pose is -1. So many of these things, some things you might understand, some things you might not. The loss which is defined, loss 3, and register infos, reg0, reg1, reg2, reg3. And then in index 2, the device on CPU, it is going to run the subgraph loss 3 classifier, and it's going to run on CPU. So that's how you can study the different X model files, and again, it's an important thing how to use this xdpu util. So finally, like, whatever I had to teach in theory, like, now all of these things which you'll study will be just like a replication of the things which we have studied. And regarding the setting up of the target, so we've already chosen the pre-built image, so which has all these things already installed on it. Like, we've downloaded the pre-built image for KV260, so, and we've burned that image. So it has the pre-built thing, everything which is installed, but the Vitis AI runtime package and the Vitis AI library samples and models are compiled into pre-built Vitis AI boards. Therefore, you do not have to install the Vitis AI runtime package when the target is used as a Vitis AI pre-built image. However, you can still install the model on a custom target, like if you build a Peta Linux image yourself, and you have to do that. So all these things have been done for us, but like, it is telling us how you can actually create that. So for each of these models which it creates, we'll have to put that inside this Vitis/user/share Vitis AI library models. But for us, it's already present and everything is available for us, including the proto-text file and everything. So the proto-text file is defining the mean, the scale values, the model type classification, top K, test accuracy, and since it's not made like nothing is mentioned here, so it shows that it's trained on actually cafe network, cafe frame. This one is trained on TensorFlow, so you can actually like see the differences in mean values and the certain scale values. So all this information, all this knowledge is quite inherent and like very eccentric to the model which we're running. So we'll have to figure it out for each model which you are actually trying to run. And you can run the Vitis AI runtime packages, and you can upload it to the board. All these things have already been installed for us, so you don't need to worry about anything, and you just have to simply now try running the Vitis AI library example. So they have provided us two files, the image file and the video file. So we'll just quickly download these two files. They are not available with us on the board itself, so I'm just copying it onto the host machine as of now. And once once the images are downloaded, this might take little time, but images I think will be downloaded more quickly. I'll just pause this so that I am able to download this more quickly. While they're getting downloaded, I'll just close certain things which are not required. So right now we're in this classification task on my host computer. I don't think I'll be compiling right now on my computer. That will be a task for you to actually try it out using the cross compiler, like OpenCV thing which you have to install. In my Kria board as well, so I've opened this whole complete folder. So instead of this, I'll just open the /home/root folder. And this is where I have to actually upload that. So that /root folder is not required as of now for my thing for exploration. So I've just opened this thing itself. Okay, so the images have been actually installed, and let me close down this and install it once again, the videos tar.gz file. And for this save, yes. So I can quickly do if I have to upload certain thing here, I can either choose this SCP command and then I have to enter the IP of the board. But with VS Code, everything everything becomes easy. I can just drag and drop into this and can upload the file. So I'll just show you the contents of the file first, so you exactly know where to place that file. Home, downloads, and this is the file, the tar.gz file. So it has samples. Inside samples, if I open, let's say, the classification task, then it has the PNG images. And if you see the structure of it, it has samples and samples on X. So it is exactly like placing this thing here, and once I extract it, do the tar.gz here, then the files will go to their appropriate memory locations. So I'll just drag and drop it inside this Vitis AI. So it's copying the file. Copying the file over the network actually. It's the same as doing the secure copy SCP, but now the VS Code is managing it for us, the copying and downloading and everything. So that's why I'm recommending you to actually set up, interact with your board using VS Code. It will help you a lot and save you a lot of time instead of typing the necessary commands. And just to let you know a little bit more about this SCP command, you can secure, you can do copy, like CP command is for copy. So you can do SCP command from any place to any place inside your network. And that is how, like, if you're there in the industry, many times you'll have to pull certain, like, copy file from one IP address to another system and run it there. So you can use SCP commands for all those things. Let's check the progress. So till that time, like, we'll utilize that time while it is getting copied, and we'll in fact do tar-xvzf, the same command which we have to use for extracting the images and videos there. We'll do it here as well, and the name of the file is Vitis AI. One is the images.tar.gz. So it has copied all of these files, and in the downloads. So I'll just actually call new folder, call it images, and place these two files here. Then inside the videos folder, I will place the videos.tar.gz file, and I'll do cd videos, and here I'll execute the same thing, but this time for videos. So we'll quickly see that what these different videos and the sample images originally look like, and then once we run the machine learning model, how do they look like. I'll go inside the images, let's go inside the samples, and if I click on, let's say, face detect, so you can actually see it in the rendered view itself, that how these images look like. And there are certain more examples of face detect for calculating the performance, like if there's this list which you perform, file which you give, then it will do the same machine learning model on these images. Similarly, for lane detect, you see that there is a relevant image for lane detect. For mono depth, like for finding the mono depth, I don't know what exactly do they refer by mono depth. For pose detect, you see that it has given a file of like something which is relevant for detecting the pose. For segmentation also, it has given sample segmentation image where we can segment all these things. Sample ultra fast, I don't know what the purpose of this is. Obviously for YOLO v3, and it will be like standard object detection things which you will see inside here. So sample YOLO v2.jpg, and segmentation, I've already shown it to you. So all these things you can actually center point, I do not know what, so it's, I don't think it's an image, which it's a text file that we have to find out the center point of all these coordinates, it seems like. For face landmark, they've given a close-up of the face. So all these things like are available, and inside the videos apps, we can actually they have given two files to us. So let me open with other application videos, let's see if, okay. So this is the video on which we can run the lane detection thing on our using the model. Obviously you do not know the the complete details of the model in itself, but you have an idea that how these models are constructed based on the PowerPoint, the lecture 2 which we had seen about VGG16, Inception Net, and how these different convolution based on computer vision tasks, all these things are all made. So I'm guessing now it has downloaded all the file. So yep, the Vitis CI thing is ready, and we could have simply done a wget here as well. But alright, let's go inside the Vitis AI examples, and here if I do an ls operation, cdy library, and here if I execute tar-xvzf, XVZF. So, and give this Vitis AI library images star.gz. So it is unpacking the same things which we are seeing there, like it is doing here as well. Obviously, this unpacking which it is doing, it is using the processor of the FPGA board. Certain, it would have been nice if we actually run this and observe how the bokeh application, how this is affecting the performance. It has already done all these tasks, so we're a little late in calculating it, but you would have seen a spike in the memory usage. You can see that this total in KB used in KB, all these things have increased, and total free memory, it was somewhere around 3 initially, is now reduced to 1.8. Okay, so now we have to go inside. Let's first of all try the face detect example itself. So CD samples and CD face detect. Here also I'll go inside samples, face detect, and you see that we have the sample face detect.jpg file with us. Now we'll run our model inside this. So you see that we already have this executable with us already available because it's pre-compiled to us. So if we just go to the readme file and we execute this command, so it has given us an output by this name, and here you can see the faces have been detected properly. I can even take a snapshot of my photo right now and can upload it, and I can see the results coming. Obviously it has to be, the image has to be of the correct dimension, but that I think the pre-processing step, even if it is not of the correct dimension, the pre-processing step should actually reduce it down to 224 cross 224 cross 3 as we had seen, right? And we're using dense box, so it's actually 320 cross 320 which it is using. It might be defined in the prototext file or the X model file, like of this dense box, whatever it is, it must be defined somewhere. Since I'm curious right now to know, so I'll just quickly, what I'll do is I'll go to code/user share Vitis AI library models dense box 320 cross 320 and what all files are available. So I'll just open the, actually I'll do an ls operation here first to see which all files are present, and then to x dpu util if x model hyphen l, if I pass in this file along with the x model file's name, which would be densebox.x model. So I can just actually control N and can copy paste it here. So you see that the input tensor is of size 320 cross 320 as the name itself has suggested, right? So the post processing step has to be proper and all those things are actually accounted for. So we could have easily compared this XDPU util with another XDPU util and see the number of subgraphs, like here it is index 1 and the register info seems like the same to me, and index 2, so there is another index 3 out here as well, like there it was up till index 2 itself. So subgraph, pixel convolution, tiled, fixed, BB output, so all these things are referring something which, like if you want to discover, we can explore and figure it out, but as of now it's not important for us. Okay, so and you can see the same DPU architecture and the fingerprint is the same, and the name of the subgraph which is executing. So it's just an interesting thing, and that's how you can actually run any machine learning code which you see here available. And in fact, on their page itself, oh yeah, now it might be an interesting time to actually do a performance test and see the performance and how the things spike up when we are actually running something. So let's do the performance test of phase detect. Is there a test performance function? Yeah, there's a test performance list and a test performance function as well. So I'll just create the command for that. I'll quickly pick up the reference from the readme file of classification. So here they have, I guess, performance they have given. It's in fact it is right here itself. So the test performance phase detect, and I hope test performance phase detect we'll pass in the machine learning model so it can accept these two models it's only. So let's pass this, and this time let's pass in this list file. So I'll just copy the file name. So I'll copy and I'll paste it here. And now we'll just so you see that it is running on the CPU utilization is also heavy because certain CPU tasks are running. Obviously we cannot see the DPU utilization, but the power you can see has spiked up. The power has definitely spiked up, and as soon as it is I think the operation must have got completed. Yep, it has got completed. So we have got FPS of 535 and some DPU mean of this, E2E mean this one, and we must have got the results also stored somewhere. Okay, we've not saved the results, we've just calculated, but we've not saved the results with the test performance code. So you can modify the CPP file which is actually running. So it's a very simple thing. It's just as we have told inside, it's just the library sample file. The main code which it is calling, what it is actually calling is which is something present inside the source folder, like the base like the libraries, the model libraries. Right, so that clarity has to happen, and we'll explore this C code more in our coming time, and we'll put benchmarks and do. So now you'll based on so just like this we've executed. There are many other things for you to try out, and they have defined all these classification tasks, post detection tasks, and play detection tasks. You can run any of these, and that will be your task. Actually, each of you would be getting a different thing to run, and you'll have to upload that code, and you'll be assigned marks based on that. So that is it for this video, and yep, watch out for the next lab session. I hope you got to learn. Thank you so much.